Welcome, everyone. For today's prep, we're going to be looking at calculating limits using algebraic methods. So far we've looked at graphical methods, we've looked at numerical methods, now we're going to be getting it more into the algebraic side of things. And what we're going to see is, in a lot of cases, it comes down to just two basic limits, the limit of a constant function and the limit of the identity function. So we're going to talk about these two basic limits a little bit more in class. But the idea is we are going to have a whole bunch of limit laws. So we're going to take a function, and with these limit laws, we're going to kind of break that function down into just those two basic limits, constants and x, identity function. So we're going to just kind of work with these limit laws first, get a little practice with these, and then in class we'll go back to those two basic limits. All right, so what is this laundry list of limit laws? Well, let's look at the first one. Let's suppose, and this is the constant multiple limit law. So let's look at this first one. What does it say? Well, we're doing the limit as x approaches a of this function where we have a variable piece, f of x, times a constant k. So we have this constant multiple k that's multiplying the function f of x. We want to do the limit of the whole thing. Well, what this limit law tells us, how we can use this limit law, is essentially we can focus on just doing the limit of the function, the variable part, the f of x, calculate the limit of that, and then multiply the result by k. So it's almost like we can take this constant k, this constant multiple, and we're moving it out in front of the limit sign. So that's one of our limit laws. The last four here tell us what happens if we have addition, subtraction, multiplication, and division. And it turns out limits work really nicely with these, with these algebraic operations. So for like the first one here, if we're calculating the limit as x approaches a of this whole big function, f of x plus g of x, well, what this limit law tells us is we can kind of split up the limit. So we can do the limit of just the function f of x, the first part here, just do the limit of that as x approaches a. Then we can do the limit of the second part, do the limit of the g of x as x approaches a, and then just add those two results together. So we can essentially split up the limit right where we see that addition sign. So we calculate two separate limits instead. And then the same thing with subtraction. If we have subtraction, we can split that up into two separate limits. If we have multiplication of two functions, well, what can we do? We can do the limit of the first function, do the limit of the second function, and then multiply the results. And even the same thing if we have a fraction, if we have a quotient here. If we have a division sign right there in the middle, well, what we can do is split it up, do the limit of just the top function, and then limit of just the bottom function, and then divide the results. So limits, calculating limits, work really nicely with addition, subtraction, multiplication, and division. And that's kind of what these limit laws are telling us. Let's just make note of this. So essentially we can just split up a limit. At any addition, subtraction, multiplication, or division that we see. Now we have one other limit law here, limit of a power function. And it turns out limits work really nicely with power functions as well. So if we have this whole big power function, f of x being raised to some power, and we want to calculate the limit of that as x approaches a, well, it turns out that we can actually kind of move this limit sign right inside that power function. So we can do the limit of just kind of like the inside variable part. And then once we have that variable, or once we have that limit all calculated, then we can raise it to the power r. Now, there are some restrictions on this one because, we have to be careful of exponents. If we have like if this was like a root function, so raised to the 1/2, we can't have negatives under a root sign. So you just have to be a little careful with this one. And the one we're going to see quite a bit that does present some issues is actually this quotient. So there is an exception to the rule here, and that is, for this one, the limit of g of x as x approaches a cannot be 0. So that limit of a quotient, we can split it up as long as we're not eventually dividing by 0. So we just have to be careful with division by x's. All right, so let's see how these limit laws actually work. So we're going to try an example here. Example 1. So we're going to evaluate this limit, and we're going to justify each step using our limit laws. And we have this function f of x kind of buried inside this whole expression that we're going to do. So we're going to use the limit laws to basically unravel and get it down to, we're going to kind of drill through the function here until we get down to bedrock here, f of x. And the way f of x is described here is with the graph of a function. So we'll kind of save the graph until we need it. But let's start using the limit laws to kind of break this function apart, to break this limit apart. So let's use our first one. So when we look at this thing, what do we got? Well, we have 3 times this function f of x, but that function f of x is getting squared, and then we're also adding a 5 on to the end. All right, so what do we got? Well, there's really the main operation here. The thing that's happening last is this plus sign that's right there in the middle. So when I look at this, we got this piece, and then we got a plus 5 at the end. So we have this addition sign in the middle, so let's use our sum law for limits that allow us to break this apart into 2 separate limits based on where that plus sign is. So we'll have the limit of 3 times f of x squared, limit as x goes to 2, plus the limit as x goes to 2 of that constant function 5. And this is the sum law. So we're just going to justify that step. All right. So what do we got next? Well, we've limit of 5. That's a constant. So we've already reached kind of one of these basic limits here. The limit of a constant is just the constant. So we're good with that 5. So we got to keep working on this this other piece. There's more algebra there to unwind. So the next thing we see is we have this constant multiple 3, and it's multiplying this f of x squared. So we got to use our limit law for that constant multiple. So we're going to bring that 3 right out in front. Okay. So, what law did we use there? That was our constant multiple. So what did we do? Essentially, we took that 3 that was a constant multiple, moved it out in front of the limit, and now we just have to do the limit of that f of x squared. All right. So there's still a little bit more going on here. We haven't made it all the way to the center yet. We got a little bit more to go. We gotta unravel this power function now. So we have this kind of outer power piece, and then we have the inner f of x here. So we gotta break our way through that power function. So let's see. What did our power rule? I think we had one up here. Yeah. Limit of a power function. What can we do? We can essentially take that limit and bring it inside of the power function. So let's see what that's going to look like. So we're still going to have that 3 in front. And then I'm going to bring this limit sign inside the parentheses there. So we're going to have our parentheses of the thing getting squared, but now we're going to essentially bring that limit right on inside. So that's our power limit law. And at this point, we've kind of gone as far as we can go. There's no more algebra to unwind with this constant 5, and there's no more visible algebra to unwind with this function f of x. We've kind of reached as far as we can go here with the the algebra that's happening in this expression that's actually visible to us. So we've kind of gone as far as we can go with our limit laws. And now we just need to know, what is the limit of f of x as x approaches 2? And this is where the graph comes in. So if we go to our graph, here's the graph of f of x. And we're interested in what's going on right around x equals 2 here. So we find 2. Now we're going to do this with our graphical methods. We find x equals 2, and we know that we have to consider what's going on a little bit to the left and a little bit to the right. So we got the left side, we got the right side, and then we just see what's happening. So on the right side, as we move along our curve, it looks like we're getting closer and closer to this point right here. So again, with graphical limits, we imagine standing on the curve, and then we're just walking closer and closer. We're kind of following the curve as x is getting closer to 2. And it looks like we're going to this point right here. It looks like that's the destination. And then if we go to the right side, again, we want to kind of see where the path is taking us. So we find the right side, go onto the curve, and then we're just going to follow that trail, and it looks like it's taken us to this point right here. So it looks like we're going to the same point. So that means the limit exists. And the value of the limit is whatever this y value is. So in this case, we'll just make note of it. The limit of f of x as x approaches 2 is equal to -2. So now we can just fill that in. So we know what this is. So we fill in the result, and we get 3 times -2 squared. And then what's the limit of 5? Well, this is one of our basic limit laws. Limit of a constant is the constant. So the limit of 5 is just 5. And if we do the arithmetic there, we end up with, 3 times 4, which is 12, plus 5, 17. All right, so we're going to look more at this in class with these limit laws. But this is kind of the idea. These limit laws allow us to, when we have this complicated expression, they allow us to kind of unravel all of the arithmetic that's going on. So we were able to break up the addition. We were able to deal with this constant multiple. We were able to deal with this power function. And we kind of make the limit go all the way through into like the heart of the function here. And that's going to be the same kind of strategy we use for, more conventional expressions like what we're going to see in example 2. So we're going to save that one for class. So we'll see you then. Bye-bye.